This is our second video about symmetric groups. In this video, we're going to work through some more advanced examples, and we're going to work our way up to a rigorous definition of the alternating groups. I'm going to start with several examples that I'm going to categorize under the heading Useful Facts about the symmetric group of degree n. You'll see later on why these examples are useful, but even just knowing how to prove them is a good test of whether or not you understand the details that we've covered so far about symmetric groups of degree n. So the first fact is that the symmetric group of degree n is generated by the collection of all transpositions of the form ij, where I and j go from 1 to n. Remember that this means that every element of the symmetric group can be written as a product of transpositions and their inverses, but since this is a finite group, and also since the inverse of a transposition is just the transposition itself, that's the same as saying that every element of Sn can be written as a product of transpositions. Okay, so how do we prove this fact? Well, the first thing that we want to observe is that by the cycle decomposition algorithm, every element of the symmetric group of degree n can be written as a product of cycles. Therefore, if we can just show that every cycle is a product of transpositions, that's going to imply that every element of Sn can be written as a product of transpositions. So let's focus on just showing that every cycle can be written as a product of transpositions. Okay, well, instead of jumping straight to the answer here, let's try to explore a little and see how you would even figure out how to write cycles as products of transpositions. So we'll start with the simplest case, which are one cycles. But remember that one cycles are just another way of writing the identity element. And since the identity element is the empty product of transpositions, one cycles can definitely be written as products of transpositions. Well, next let's think about two cycles. Two cycles are transpositions, so they're also definitely products of transpositions. And now let's come to the first interesting case, which is the case of a three cycle. So let's suppose that we have a three cycle, A1, A2, A3, and let's think about how we would try to write this as a product of transpositions. I want to emphasize that there's more than one way to do this, and that's kind of an important fact, which is going to come up in a major way later in the video. But for now, we're just trying to find one way of writing this as a product of transpositions. Okay, well, one natural thing that you could try is to start by noticing that this map maps A1 to A2. So we could try to start out with the transposition that interchanges A1 and A2. Now this transposition by itself moves A1 to the correct position, but it moves A2 to A1 instead of to A3, so we still have a little more work to do. Well, if you think about it, if A2 moves to A1, and your final goal is to get A2 to A3, then what you can do is you can left multiply the transposition A1, A2 by the transposition A1, A3. The product of these two transpositions is going to first move A2 to A1, and then it's going to move A1 to A3, with the net effect being that it's going to move A2 to A3. Remember, as we mentioned in the last video, that when you're trying to figure out where elements go, when you apply products of permutations to them, you should always work starting from the right and working to the left. Well, now we have a product of two transpositions that maps A2 to the correct place, but we need to be careful to make sure that we haven't messed up anything else, and we also need to check to make sure that it maps A3 to the correct place. So let's just go through it really quickly. First of all, where does A1 map to? Well, the rightmost transposition maps A1 to A2, and the leftmost transposition fixes A2. So the net effect is that A1 gets mapped to A2, and that's what we wanted. We already checked that A2 maps to A3, and that's also what we wanted. And so what about A3? Well, the rightmost transposition fixes A3 and passes it directly to the leftmost transposition, which then maps it to A1. So the net effect is that A3 gets mapped to A1, which is again what we wanted. That means that the three cycle A1, A2, A3 is the product of the transpositions A1, A3 followed by A1, A2. And that shows that every three cycle can be written as a product of transpositions. Well, now it feels like we're getting somewhere, so let's try to figure out next how to write four cycles as products of transpositions. Well, if we learned something from the previous example, then we might start by taking a four cycle A1, A2, A3, A4, and writing it as a transposition which interchanges A1 and A4, followed by a three cycle which moves A1 to A2 to A3 and back to A1. Now, once again, you need to go through and check that all of the AIs here map to the correct places, but that's not too difficult to do. So A1 maps to A2 and then it's fixed by the transposition. A2 maps to A3 and then it's fixed by the transposition. A3 maps to A1, which then maps to A4. And A4 is fixed by this three cycle and then mapped to A1 by the transposition. That means that the 4 cycle on the left is equal to the transposition times the 3 cycle on the right. Well, now we've discovered a general pattern, which I hope you can see is going to help us with our final goal of showing that every cycle can be written as a product of transpositions. We already know how to write this 3 cycle A1, A2, A3 as a product of transpositions. And so inserting that information in here, we now know how to write every 4 cycle as a product of 3 transpositions. Well, continuing in this way, we can show by an inductive argument how to write any k cycle for k bigger than or equal to 3 as a product of transpositions. And the starting point is to take a k cycle A1 to AK and write it as a product of a transposition which interchanges A1 and AK, followed by a k-1 cycle A1 to AK-1. Now once again, it's pretty easy to see that this product of cycles is equal to the k cycle on the left. And if you think about it, because the transposition A1AK only moves the points A1 and AK, but fixes everything else, we don't really need to check everything here. Unless the transposition is fed an A1 or an AK by the k-1 cycle on the right, it's not going to actually do anything. So here we see that A1 maps to A2, but assuming that k is at least 3, A2 is fixed by the transposition, and similarly A2 maps to A3, and so on until I get down to AK-1. Well, now AK-1 is mapped to A1, but the transposition then moves that to AK, which means that the net effect is that AK-1 gets mapped to AK. And finally, what about AK? Well, the k-1 cycle on the right doesn't do anything to AK, but the transposition moves it to A1. So that shows that all of the elements A1 to AK get mapped to the correct place, and the k cycle on the left is equal to the product of the transposition and the k-1 cycle on the right. Well, at this point we can continue in this way and write this k-1 cycle as a product of transpositions, A1 AK-1, A1 AK-2, all the way down to A1 A3 and A1 A2. That shows that every k cycle can be written as a product of transpositions, and it completes the proof that the symmetric group of degree n is generated by the collection of all transpositions. The next thing that I want to convince you of is that you don't need to start with all of the transpositions in order to generate Sn. It suffices just to start with the collection of transpositions of the form I plus 1, where I is bigger than or equal to 1 and less than n. This subset of the collection of all transpositions by itself generates all of Sn, so that every element of Sn can be written as a product of transpositions of this special form. Now, in order to prove this, let's let H be the subgroup of Sn generated by the collection of all transpositions of this form, so that what we're trying to show is that H is equal to Sn. What we're going to do is show that every transposition of the form Ij, where I and j are arbitrary elements from 1 to n, can be written as a product of transpositions of this special form I plus 1. If you can get all transpositions as products of transpositions of this special form, then since Sn is generated by the collection of all transpositions, that's going to imply that Sn is also generated by this subset of the collection of all transpositions. So to start with, you need to do a little experimentation and play around with products of transpositions of this form to try to understand how you might be able to write all possible transpositions as products of transpositions of this form. But after some experimentation, you might notice, for example, that when you multiply 2, 3 times 1, 2 times 2, 3, which are all transpositions of this special form, then you end up getting the single transposition 1, 3. And we can go through and check this really quick if you'd like. So consider the product of the 3 transpositions on the left. What does it do to 1? Well, the rightmost transposition doesn't do anything to 1, and the next transposition moves it to 2, and then the next transposition moves that 2 to 3. So the net effect is that 1 gets moved to 3. Well, now what happens to 3? Well, the rightmost transposition maps it to 2, and then the next transposition maps that back to 1, and the last transposition doesn't do anything. So 3 maps back to 1. And how about 2? Well, the rightmost transposition maps 2 to 3. The middle transposition doesn't do anything to that 3. And then the leftmost transposition maps the 3 back to 2. So the net effect is that 2 is fixed. Any other integers from 1 to n don't appear in this product, and so they're obviously going to be fixed by this product of transpositions. Therefore, the product of these transpositions is the transposition 1, 3. And since we started with 3 elements which we knew were in the generating set, that allows us to conclude that the transposition 1, 3 is also an element of the group H generated by this collection of transpositions. Well, now we can play the same game again, and we can put 1, 3 in the middle here, and left and right multiply by 3, 4. Now the calculation is very similar, and you'll find that when you multiply these three transpositions together in this order, you end up with the single transposition 1, 4. And so once again, since we started with three elements of H, when we multiply them together, we're going to get another element of H. So our conclusion here is that 1, 4 is an element of H. By the way, this is all assuming here that n is bigger than or equal to 4, but if n is smaller than that, this is still a true statement. We're just trying to deal with the general case here. Anyway, if we continue in this way, we can put the transposition 1, 4 in the middle, and left and right multiply by the transposition 4, 5 to find that 1, 5 is an H. And continuing in this way, we end up getting that 1j is an H for every j from 2 up to n. So that takes care of all transpositions of the form 1, j. Now, we can play exactly the same game, starting with any transposition of the form I plus 1, where I is bigger than or equal to 1 and strictly less than n minus 1. If we take this transposition and left and right multiply by the transposition which interchanges I plus 1 and I plus 2, then we find that we get the transposition which interchanges I and I plus 2. And so, because we started with the product of three elements of H on the left-hand side, we conclude that the element on the right-hand side is also an element of H. Well, now, continuing in this way, if we put I plus 2 in the middle and left and right multiply by the transpositions which interchange I plus 2 and I plus 3, we find that the transposition which interchanges I and I plus 3 is also an element of H. And continuing in this way, we find that all transpositions of the form ij, where j goes from I plus 1 up to n, are elements of H. Well, the I here was arbitrary, so that proves that H must contain all transpositions. But if H contains the set of all transpositions, then it must also contain the group generated by that set. And we know from part 1a that the group generated by the set of all transpositions is all of Sn. That allows us to conclude that the group H is in fact Sn, and it completes our proof that Sn is generated by this special collection of transpositions of the form I plus 1, where I is bigger than or equal to 1 and less than n. Our next important fact, which may seem kind of surprising at first, is that for n bigger than or equal to 2, Sn is actually generated by the set consisting of just the transposition 1, 2, and the n cycle 1 through n. To see why this is true, as before, let's let H be the group generated by the set consisting of these two elements. And what we're going to aim to show this time is that every transposition of the form I plus 1 is an element of this group H. That, together with the result of example 1b, will imply that H is equal to all of Sn. So in order to do this, let's first of all compute what the inverse of the n cycle 1, 2 to n is. This n cycle maps 1 to 2 to 3 all the way down to n and back to 1, so the inverse of the n cycle is just what you get by reversing the order of the entries. In other words, it's the n cycle that you get by mapping n to n minus 1 all the way down to 2 to 1 and back to n. Now, since groups are closed under taking inverses, and since the n cycle from 1 to n is an element of the group H, I know that this n cycle must also be an element of H. Well, first of all, I like to think about what happens when I take the 2 cycle 1, 2, and left multiply it by the n cycle from 1 to n, and right multiply it by the n cycle from n down to 1. Pay attention to the fact that the 2 cycle here just interchanges the points 1 and 2 and fixes everything else. So if it gets past anything except for a 1 or a 2, it's just going to feed it directly into the n cycle on the left. But the n cycle on the left and the n cycle on the right are inverses of each other. So if something comes out of the n cycle on the right and just gets passed directly to the n cycle on the left, it's just going to get moved back to where it started. And that simplifies the number of things that we need to think about here. So for example, if n is bigger than or equal to 4, say, and I want to know what this product of cycles does to 4, I first of all look at the rightmost cycle, and I notice that it moves 4 to 3. Well, that 3 gets fed to the transposition in the middle, which passes it directly to the n cycle on the left, and then the 3 gets moved back to 4 where it started. So the product of these cycles is going to fix anything that doesn't get moved to a 2 or a 1 by the cycle on the right-hand side. That means that to understand what this product of cycles is doing, the only inputs that I need to think about are 3 and 2. Well, let's start with the 2. The cycle on the right-hand side here moves the 2 to a 1, and then feeds it to the transposition in the middle, which moves the 1 to a 2, and then feeds it to the n cycle on the left, which moves the 2 to a 3. So the net effect is that 2 gets mapped to 3. Now how about 3? Well, you may have already been able to deduce this from what I said, but let's just go through it. The n cycle on the right moves the 3 to a 2, and then the transposition in the middle moves the 2 to a 1, and the n cycle on the left moves that 1 to a 2. So the net effect is that 3 gets moved to 2. and that means that the product of these three cycles is actually the transposition 2, 3. Now, since I took a product of three things that I already knew were in H, I can conclude from this calculation that the transposition 2, 3 must also be an element of H. Well, now, repeating this same calculation with the transposition 1, 2 in the middle replaced by the transposition 2, 3. An exactly analogous analysis shows that the product of these three cycles produces the transposition which interchanges 3 and 4. So now I know that the transposition which interchanges 3 and 4 is an element of H. And hopefully now the rest of the proof is somewhat clear. I can continue in this way all the way down the line until I get to the transposition n-1n. And now we've shown that all of the transpositions of the form I plus 1 with I bigger than or equal to 1 and less than n are elements of H. Therefore, the subgroup that this collection of transpositions generates must also be a subset of H. But we showed in 1b that this subset generates all of Sn, so that allows us to conclude that H is actually Sn, and that's exactly what we were trying to show. So now we've whittled this down to show that Sn, even though it's a complicated group in general, is always generated by the set consisting of these two elements. In other words, every element of this group can be written as a product of finitely many copies of these elements. Now I want to talk about alternating groups, and I'd like to do this carefully. It's easy just to crash through the definition, but there are some details here that I think are worth paying attention to. So first of all, let's start with a seemingly innocuous definition. So a permutation sigma in Sn is called odd if it can be written as a product of an odd number of transpositions, and it's called even if it can be written as a product of an even number of transpositions. Now, that seems pretty straightforward, so let's look at a few examples just to make sure that we understand the definition here. Here are 4 different permutations, say in the group S4, and let's try to decide whether these permutations are odd or even, or maybe both. Well, first of all, the identity map can be considered as a product of 0 transpositions, or if you want, it can be considered as a product of any transposition times itself, since every transposition is the inverse of itself. So thinking about it either of those ways, we see that the identity element is even. Now, of course, a transposition is just a product of 1 transpositions, so a transposition is going to be odd. And now, if you followed along with the previous proofs, then the next 2 examples shouldn't be too difficult here. So for the first one, we saw that we could write a 3-cycle, say 1, 2, 3, as a product of 2 transpositions. And since 2 is an even number, that shows that a 3-cycle is always going to be an even permutation. Now, what about if I multiply together a 3-cycle and a 4-cycle? Well, I know that I can write the 3-cycle as a product of 2 transpositions, and also that I can write the 4-cycle as a product of 3 transpositions, and the total number of transpositions in the product on the right-hand side is 5. So, since 5 is odd, a product of a 3-cycle and a 4-cycle is always going to result in an odd permutation. Okay, well, there's a hidden question lurking here, which is not trivial to answer. So in order to uncover it, let's make a couple of observations. First of all, we already showed in our examples at the beginning of the video that every element of Sn can be written as a product of transpositions. So by our definition, that guarantees that every element sigma of Sn is going to be even or odd. But by this point, we also know that as long as n is bigger than or equal to 2, there are always infinitely many ways to write any element of Sn as a product of transpositions. So for example, the identity element is 1, 2 times 1, 2, or the transposition 3, 4 is 1, 2 times 3, 4 times 1, 2, and so on. And so the question here is it possible that there's an element of Sn which could be written both as a product of an even number of permutations and as a product of an odd number of permutations? In other words, we already know that every element of Sn is even or odd, but the question is, can an element of Sn be both even and odd? Well, it would be easy to brush this under the rug and keep going, but I'd like to convince you that this can't happen. So let's write this as a theorem and let's try to prove that every element of Sn is either even or odd, but not both. Now, we've already got the first half of this done. We know that every element of Sn is either even or odd. So what remains is just to show that an element of Sn can't be both even and odd. Well, for the proof, for every element sigma in Sn, let's define kappa of sigma to be the number of cycles in the cycle decomposition of sigma, plus the number of integers I from 1 to n, with the property that sigma of I is equal to I. In this definition, we're relying on the cycle decomposition theorem, which remember tells us that every element of Sn can be written as a product of disjoint cycles, and that that product is unique up to the order in which the cycles appear. That guarantees that the first quantity in this definition is well defined. Now the second quantity is also obviously well defined, and I want to mention for reference that a point I with the property that sigma of I is equal to I is called a fixed point of the permutation sigma. Well, the proof that we're going to give hinges on a fact which I'm going to state here as a claim, that for any permutation sigma and for any transposition, when I multiply the transposition times the permutation, I either increase or decrease the quantity kappa by 1. The proof of this theorem is going to follow relatively easily from this claim. So first let's take a look at the proof of the claim. We're going to divide the proof of the claim into two cases, which correspond to the two possibilities for the value of kappa of the transposition times the permutation. The first case that we're going to consider is the case when I and j both appear in the same cycle in the cycle decomposition of sigma. And in this case, there are 4 different forms that cycle can take. First of all, it could be that the cycle is just the transposition that interchanges I and j. Or it could be the case that cycle moves I to a1 to a2 out to ak for some natural number k, and then back to j and then back to I. Or it could be the case that I goes to j and then j goes to b1 to b2 out to bl for some natural number l, and then back to I. And finally, if I and j both appear in the same cycle in the cycle decomposition of sigma, and if that cycle doesn't have one of the first 3 forms here, then it must be the case that the cycle has the form I, a1, a2 out to ak for some natural number k, followed by j, b1, b2 out to bl for some natural number l. One thing to remember here, which we mentioned in the previous video, is that the cycle notation of a single cycle of length at least 2 is never unique. So when I'm writing down a cycle, I can choose any one of the entries in the cycle to be the first entry. And here I've decided to choose I to be the first entry in all of these representations. Well, anyway, these are the 4 possibilities for the cycle in which I and j appear in this case. And now let's think about what happens when we left multiply each of these possibilities by the transposition ij. First of all, when I take the transposition ij and I left multiply it by ij, I just get the identity back, because a transposition is an element of order 2 in the symmetric group. So when I square it, I just get the identity. Now, in the second case here, when I multiply ij by a cycle of the form I, a1 out to ak and then j, what am I going to get? Well, first of all, let's just think about where I maps to. The cycle on the right-hand side moves I to a1, and then since a1 is not equal to I or j, the transposition on the left doesn't do anything to the a1. So the net effect is that I maps to a1. Now similarly, a1 is going to map to a2, which is going to be left alone by the transposition, and so on all the way down the line, until I get to ak minus 1, which is going to map to ak. Now ak is going to map to j, but then the transposition on the left is going to map that j back to I, so that's going to close this cycle. And now the final thing that we need to think about is what's going to happen to the j. Well, the cycle on the right-hand side is going to map j to I, and then the transposition is going to take that I and map it back to j. So that means that after I multiply together the transposition and the cycle, j becomes a fixed point. Now the third case is very similar to the second case, so I'll let you work out the details of that one. But in this case, when you multiply together the transposition and the cycle, you end up just removing I from the cycle and making it a fixed point. In the final case, the situation is a little different. So in this case, let's start by thinking about what happens to I. Well, once again, I maps to a1 and a1 is fixed by the transposition, so I maps to a1. And then a1 maps to a2, which is fixed by the transposition, and so on all the way down to ak. So that gives us the beginning of a cycle here. And now ak maps to j, but the transposition maps j back to I. So that's the end of that cycle, and it's a k plus 1 cycle. Well, next we need to think about what happens to j. And j maps to b1, which is fixed by the transposition, so that means that j just maps to b1. Well then, b1 maps to b2, which is fixed by the transposition, and so on all the way down the line, until we get to bl minus 1, which maps to bl. Now bl maps to I, but the transposition maps I back to j, so that gives us an l plus 1 cycle that starts with j and ends in bl. So the effect in this final case of left multiplying by ij is that we split apart the original cycle that contained I and j into 2 new cycles. Now, the final thing to note about this is that all of the other cycles in the cycle decomposition of sigma are disjoint in this case from I and j and from all of the a's and b's. So left multiplying by the transposition ij doesn't affect the number of fixed points or cycles besides the ones that you see listed here. Well, now let's go through each one of these 4 possibilities and see what happened to the number of fixed points and the number of cycles in each case. In the first possibility, we started in a situation where I and j were in the same cycle of sigma, but we ended in a position where we removed that cycle and created two new fixed points. So what we've done here is we've removed a cycle and we've created two new fixed points. Now, in the second case, we started with a single cycle which contained I and j, and we ended also with a single cycle, but we created a new fixed point which was the fixed point j. Therefore, we just added one fixed point, but we didn't change the number of cycles. It's the same situation in the third case, except now I is the fixed point, but again, we haven't changed the number of cycles and we've just added one fixed point. And finally, in the last case here, we haven't created any new fixed points, but we've taken the original cycle and we've split it into two. So we end up with one extra cycle, but no new fixed points. Okay, well now think about what this means for the quantity kappa of ij times sigma. Remember, kappa of something is the number of cycles in the cycle decomposition of that thing plus the number of fixed points. So if you look at the net effect in all of these four possibilities, we see that we've increased the sum of the number of cycles plus the number of fixed points by 1. That takes care of the first case, which is the case when I and j are in the same cycle in the cycle decomposition of sigma. The second case then, of course, is the case when I and j don't appear in the same cycle in the cycle decomposition of sigma. And in this case, let's write the cycles that I and j appear in as I a1 ... ak and j b1 ... bl. Now, to be perfectly honest, it could actually be the case that I and or j is a fixed point of the map sigma. And in that case, the cycles that they appear in wouldn't look like this. So really, as before, we need to consider 4 different possibilities. But this time, let's be a little more concise and try to group all the 4 possibilities together. So let's think about what happens when we take a product of two cycles of this form and left multiply by the transposition which interchanges I and j. We'll start by thinking about where I maps to, and we can see that the rightmost cycle doesn't do anything to I, but the next cycle moves I to a1. Well, the transposition on the left fixes a1, so that means that I maps to a1. And now going through this as before, it's pretty easy to see that a1 maps to a2, and so on all the way down to ak-1, which maps to ak. But now ak maps to I, and the transposition takes I back to j. So that's not the end of the cycle here, because the net effect is that ak maps to j, so the cycle keeps going. Well, now j maps to b1, which is fixed by both of the permutations on the left, so the net effect is that j maps to b1, and then b1 maps to b2, and so on, all the way down to bl-1, which maps to bl. And then bl maps to j, which is fixed by the second cycle here, and fed into the transposition on the left, which maps it back to I. So the net effect is that bl maps back to I, which means that we end up with a single cycle on the right-hand side. Now, just as before, all the other cycles in the cycle decomposition of sigma are disjoint from these cycles. So fixed points and cycles that don't involve the I and the j and the ai's and the bi's are not going to come into the calculation of kappa. So what is the value of kappa of ij times sigma in this case? Well, here you need to remember that there really are 4 different possibilities, so to be thorough you should check all 4. But you're going to find out that in every case, kappa of ij times sigma is equal to kappa of sigma minus 1. Now this finishes our consideration of the second case. So putting the 2 cases together, we see that no matter what sigma is and no matter what transposition ij we have, kappa of ij times sigma is always equal to kappa of sigma plus or minus 1. Therefore, we've established our claim. Now that was the tricky part of the proof, and the rest is actually not too difficult. Now we're in the home stretch, so let's go for this. Let's suppose that we have a permutation sigma in Sn, and that we have 2 different ways of writing it as a product of transpositions. First of all is a1b1 times a2b2 out to akbk, and also as c1d1 times c2d2 out to cldl. Keep in mind that this actually does happen, and that what we're aiming to show here is that k and l are either both even or both odd. Well, if sigma is equal to this product and this product, then the 2 products must be equal to each other. And now what I want to do is move all of the transpositions on the left over to the right-hand side, but I need to be careful because this is a non-Abelian group, so I can't just move them over however I want. So the first thing that I do is I left multiply by the inverse of a1b1, which is just the transposition a1b1, and that eliminates the a1b1 on the left and moves it to the left-hand side of the product on the right. Then I continue and I left multiply by the inverse of a2b2, and I keep doing this until I've moved all of the transpositions on the left-hand side over to the right-hand side. That gives me the equation that the identity element is equal to the product of ak bk times ak minus 1 bk minus 1 all the way down to a1 b1, and then times c1 d1 c2 d2 all the way back up to cl dl. Well, since the permutation on the left is equal to the permutation on the right, what I'd like to do now is compute kappa of both sides of this equation and see what that tells me about the relationship between k and l. So let's compute kappa of both sides of this equation. And I want to add in an identity element here, which is not going to change anything, but which will help to clarify what happens at the next step. First of all, on the left-hand side, I have kappa of the identity element. And since the identity element is a product of 0 disjoint cycles, but has n fixed points, I have that kappa of the identity element is equal to 0 plus n, or n. Now we can understand the value of kappa of the permutation on the right-hand side by using our claim from before. So think about the big product here as starting with the identity element and then successively left multiplying by each of these transpositions. We know that kappa of the identity element is n, and when we left multiply by the transposition CL dl, we're going to add a plus or minus 1 to that. Now, if you followed what we did before, then you know that in this case we're actually going to subtract a 1, but it's not going to make a difference whether it's a plus or minus 1 here, so let me just write it as a plus or minus 1. Now, as you go down the line here, each new transposition that you introduce is going to add another plus or minus 1, and you're going to end up with exactly L plus or minus 1s. And then when you left multiply by A1, B1, you're going to add another plus or minus 1, and then continue in that way all the way down till you get to AK, BK, which is going to give you another K plus or minus 1s. Canceling the n on both sides of this equation, we have the equation that 0 is equal to a sum of k plus or minus 1s plus a sum of l plus or minus 1s. And now the final step to finish the proof is to think about this equation modulo 2. Noting that 1 is equal to negative 1 modulo 2, I have exactly k residue classes which are 1 mod 2, and exactly l residue classes which are 1 mod 2. So modulo 2, this equation says that 0 is equal to k plus l. Well, if 0 is equal to k plus l mod 2, then k is equal to negative l mod 2. But modulo 2, l is equal to negative l, so that gives me that k is equal to l mod 2. Of course, that's exactly the same as saying that if k is odd, then l is odd, and if k is even, then l is even. Therefore, once you know that a permutation is odd, you're never going to be able to write it as an even product of transpositions. So that completes the proof that every permutation in Sn is either even or odd, but not both. So now you know that when I told you at the beginning of the video that we were going to give a rigorous definition of the alternating groups, I was telling you the truth. And now we're ready to give the definition. The alternating group of degree n is defined to be the subgroup of Sn consisting of the collection of all even permutations. Now, that's always a non-empty set because it always contains the identity element, which is an even permutation. And it's also closed under multiplication, because if you have two permutations which can both be written as a product of an even number of transpositions, then when you multiply them together, their product will also have that property. Therefore, by the subgroup criterion for finite groups, An is indeed a group. Okay, well, now that we have this new collection of groups, let's first of all ask, what are the cardinalities of these groups? If n is 1, then A1 is just the trivial group, so its cardinality is 1. But if n is bigger than or equal to 2, then it turns out that the cardinality of An is equal to n factorial divided by 2, which is exactly half of the cardinality of Sn. You can probably already guess why that's true, and the proof is not too difficult. So let me just say that it follows from the fact that the map which takes a permutation in Sn to the product of the two-cycle 1, 2 times that permutation is a bijection from the collection of all even permutations to the collection of all odd permutations. This is not something which is difficult to verify, and it guarantees that the collection of all even permutations has the same cardinality as the collection of all odd permutations. But since every element of Sn is either even or odd, that means that each of these two sets contains exactly half of the elements of Sn, so that proves this claim. Okay, well, let's conclude this video by doing a few cooldown exercises. So for the first few exercises here, I want to compute An for a few values of n. And we'll start with the easiest one, which is A1. Now, we already mentioned that A1 is just the trivial group, so that example maybe was a little too easy. So now let's think about A2. Well, once again, by our formula for the cardinality of An for n bigger than or equal to 2, we know that the cardinality of A2 is 2 factorial divided by 2, which is 1. And so again, A2 must just be the group consisting of the identity element. Okay, well now let's go to A3. Here, our formula for the cardinality tells us that the cardinality of A3 is 3 factorial over 2, or 3. So we know right away that A3 is isomorphic to a cyclic group of order 3. But let's see if we can identify the elements of A3 in cycle notation, say, as elements of S3. Of course, we know that the identity element has to be in there. So what other two elements are here? Well, S3 is not a very complicated group. It's got transpositions in it, but transpositions are odd because a transposition is just a product of one transpositions. So those are not going to help us here. But of course, S3 also has 3 cycles in it, and we know from earlier in the video that any 3 cycle is a product of 2 transpositions, therefore 3 cycles are always even. So this is what A3 is explicitly as a subset of S3. Now, it's clear in this case that we've done this problem correctly, so even though it's not completely necessary, I'd like to show you how you could check your work, because understanding how to compute the number of permutations in Sn with a given cycle type is something which is important, especially when n gets larger. So how would we compute the number of 3 cycles in S3? Well, a generic 3 cycle looks like A1, A2, A3, and there are 3 choices for A1, but then once A1 is chosen, there are 2 choices for A2. And finally, there's 1 choice remaining for A3. But now we're not done, because remember that every 3 cycle has 3 different representations. So choosing A1 and then A2 and then A3 is going to give you the same 3 cycle as if you choose A2, A3, A1 or A3, A2, A1. And since there are 3 ways of choosing each 3 cycle, we need to divide our product 3 times 2 times 1 by 3. When you work this out, of course, it gives you 2. And we already knew that that was the answer, because this is a very small and easy to understand group. Okay, well now let's try to work out what A4 is, and here the situation is going to be a little more interesting. So first of all, the cardinality of A4 is 4 factorial divided by 2, which is 12, which means that A4 is going to consist of 12 elements. And now let's see if we can identify what some of these elements are. Well, first of all, there's the identity element, and now we also know that we have all of the possible 3 cycles in S4. So here are the 3 cycles, and I've tried to list them in a somewhat methodical order to make sure that I didn't miss any. But since I'm only a human, I'd like to have a double check to make sure that I got all of the 3 cycles. So I'd like to have a formula for the number of 3 cycles in S4. Well, just as before, think about how you choose a 3 cycle A1, A2, A3 in S4. You've got 4 choices for the first entry, and then you have 3 choices for the next entry, and then you have 2 choices for the final entry. But because there are 3 different ways of writing each 3 cycle, you have to divide that quantity by 3, and that means that the total number of 3 cycles in S4 is equal to 4 times 3 times 2 divided by 3, which is 8. Now here we found 8 different 3 cycles, so that means that we have got them all. But there are still 3 other elements here, so what are these 3 missing elements? They're not 4 cycles, because 4 cycles are products of 3 transpositions, so 4 cycles are odd. Well, here you need to remember that for n bigger than or equal to 4, not every element of Sn is a single cycle. So if you think about the cycle decomposition, when n is 4, there are also elements of Sn whose cycle decomposition is a product of 2 disjoint transpositions. So for example, the permutation which interchanges 1 and 2 and interchanges 3 and 4, or the permutation which interchanges 1, 3 and 2, 4, or 1, 4 and 2, 3. Well, these are all different elements of S4, and now we found 12 distinct elements of S4 which are all even permutations, so since the cardinality of A4 is 12, we know that we're done. But just for completeness, let's look at how we would actually calculate the number of pairs of disjoint 2 cycles in S4. So first of all, notice that if you have an element of S4 which is a product of a pair of disjoint 2 cycles, then once you choose what the first 2 cycle is, that automatically determines what the other 2 cycle is, since there's only 2 elements left to work with. So to count the number of pairs of disjoint 2 cycles in S4, we first of all need to count the number of ways of choosing a 2 cycle. But we also need to take into consideration the fact that if you have a product of 2 disjoint 2 cycles, sigma 1 and sigma 2, it's the same as the product of sigma 2 and sigma 1. So after we count the number of ways of choosing a 2 cycle, we need to divide by 2 to accommodate this fact. So our formula is the number of ways of choosing a 2 cycle divided by 2. And we already know how to choose a 2 cycle. First of all, we choose the first entry, and since we're working in S4, we have 4 choices for that first entry. Once we've chosen that first entry, we choose the next entry, and there are 3 choices left. But since any 2 cycle can be written in 2 ways, we have to divide that answer by 2. And finally, when we work out what this quantity is, we find out that it's equal to 3. And of course, we already knew that in this case, but this gives you a pattern that you can follow for bigger n that will help you to count the number of ways of writing a permutation with a given pattern of cycles in its cycle decomposition. Now for the final example, I just want to mention that while A1, A2, and A3 were all abelian groups, it turns out that for n bigger than or equal to 4, AN is always a non-abelian group. And we can verify this very easily. So let's let sigma be the 3-cycle 1, 2, 3, and let's let tau be the 3-cycle 1, 4, 2. Well, since these are both 3 cycles, they're products of 2 transpositions, so they're even permutations and therefore elements of AN. And you can compute directly that sigma tau is the 3-cycle 1, 4, 3, and that tau sigma is the 3-cycle 2, 3, 4. Well, sigma tau and tau sigma here are not the same, so that verifies the claim that for n bigger than or equal to 4, the alternating group AN is always a non-abelian group. Okay, well, that's the end of this video. Thank you for watching. In the next video, we're going to start talking about homomorphisms.